Yesterday, we were talking about covalent bonds and how they share electrons. And how they share electrons. And basically, the way we know this is because of the difference in their electronegativities. So, and we discussed how in order to get an electronegativity, you have to have a table with electronegativities on it. But there is a trend. So if we move down here, we talked about double and triple bonds, that if they are the same element, they are nonpolar covalent because they have the same electronegativity. For covalent bonds, the intermolecular forces between the molecules, not atoms. So intermolecular forces are between molecules. They are weaker than the intramolecular forces, and this would be between the atoms. Now, let me explain a little bit about how this manifests itself, okay? If I put sugar into water and it dissolves in the water, what breaks apart is the intermolecular forces. So the whole sugar molecule is still intact. But if I put sodium chloride, which is an ionic bond, into water, the sodium breaks off and attaches to the negative oxygen. The chlorine breaks off and attaches to the positive hydrogen. It actually splits apart. They are only held together by electrostatic forces. Intramolecular is electrostatic forces. In terms of covalent bonds like sugar, the whole molecule stays intact, but it separates from another molecule. So they are no longer attached, and so they disappear into solution. Okay? We're going to talk more about this. This is just the start of this unit, all right? So we want to address electronegativity a little bit more. In electronegativity, we're talking about the ability to attract electrons in a bond. So in other words, if I look at hydrogen and fluorine, there are 2 electrons in this bond, plus fluorine has 6 more because it has a total of 7, so the 7th one is here. What happens is fluorine has the highest electronegativity on the periodic table. So it is going to pull the electrons toward it. When it does, it creates what we call a dipole. And the dipole brings the electrons toward the fluorine. So what happens is there's what we call a partial positive charge and a partial negative charge. This is called a dipole. We're going to get there, so you don't have to write it down. A dipole. It has 2 poles. It has a positive end and a negative end due to the difference in electronegativities. So what is the difference? Well, hydrogen is 2.1, and fluorine has the highest electronegativity on the periodic table at 4.0. So this is where I'm going to take 4.0, and I'm going to subtract 2.1, and I get 1.9, and that's where you get that little range, right? The range. And this is within the range of a polar covalent heading toward ionic bond. So there is a trend, top to bottom, it's going to decrease. And the reason is because the valence electrons are getting farther away from the nucleus. Left to right, the trend, the electronegativity increases because due to nuclear effectiveness, those atoms are getting smaller. So therefore, the pull into the atoms for those electrons is greater. Fluorine has the highest electronegativity on the periodic table as 4.0, and francium has the lowest. Okay, and so remember, the ionization energy basically has the same trend. So for ionization energy, the same trend, left to right is an increase due to nuclear effectiveness. Top to bottom is a decrease due to energy levels. Yep.
Sorry, why did you say left to right?
Left to right is an increase in ionization energy.
So that's why it's going to increase in electronegativity.
Correct. They're getting smaller due to a nuclear effectiveness, so the pull into the nucleus is stronger. So all of these are tied together, right? All these trends. Okay, so arrange the following according to increasing electronegativity. So I'd like you to do that now. Okay, so the highest electronegativity is going to be farthest to the right here in my answer, and the lowest electronegativity is going to be farthest to my left because we're increasing. So the first thing I do is I take phosphorus, and I look sodium or phosphorus, which one is higher. Sodium is larger, so it has a lower electronegativity. So phosphorus currently is the highest. Then I take phosphorus and nitrogen. Which one has a higher electronegativity? Nitrogen, because it has one less energy level. So nitrogen is currently the highest. Now I look nitrogen and aluminum. Which one has a higher electronegativity? Nitrogen. So nitrogen is my largest. Next, phosphorus and sodium. I know phosphorus is the largest. Phosphorus and aluminum, so I'm going to cross this out. Phosphorus and aluminum, well, they are on the same energy level, but aluminum is farther to the left, so it is larger. It has less protons. And so because of that, it's going to have a lower flip that. Phosphorus, aluminum is farther to the left, it will have a lower, right? Did I say that? Aluminum will have a lower electron affinity. So phosphorus is next. Okay? Next, I'm going to look at sodium and aluminum. Sodium is really far over to the left, making it much bigger because it has way less protons. So sodium is going to have the lowest, and then aluminum. All right? So this is how you do it, because it's going to be, you're going to get a test. On the test, you'll get a question with 4, and it'll say, put them in order. So start with 1, choose, get through all of the other 3, which one's largest, smallest, right? Put it in the right place, just like I just did, okay? You're going to have some of those problems for homework. All right, moving on. Okay, next we're looking at bond energy. All right, that's what's next in your packet, right? Okay. So bond energy, we've already talked about it. It's the energy needed to break the bond. So it increases as the difference between the electronegativities increase. Because the greater the difference between the electronegativities, the more of a pull toward one side. So the stronger that connection. All right? So, for example, if I use carbon and hydrogen, so there's my carbon-hydrogen bond. Carbon is 2.5. Hydrogen is 2.1. So the difference is 0.4. So my partial charge is going to go from the hydrogen to the carbon. which means the hydrogen is slightly positive and the carbon is slightly negative. How much? Barely at all, 0.4. We call this polar covalent because there is a polar element to it, but the difference between them is very small. It's polar covalent, and this is generally between a nonmetal and a nonmetal. Now, metals and metals do not bond, because a positive and a positive wouldn't work. They both want to get rid of electrons, so there's no place to put them. But the negative and a negative, they can bond because they can share to complete their set. All right, let's look at chlorine and chlorine. This is going to be a 3.0 and a 3.0. The difference is 0.0. There is no dipole, and we call this a covalent bond. The electrons are shared equally. Because they're the same element. So there's no movement of those electrons. Lastly, we're going to look at sodium chloride. Sodium is 0.9. Chlorine is 3.0. The difference is 2.1. This is a large difference. There is a dipole where chlorine is going to get the electrons more for a greater amount of time, which means that chlorine has a negative charge and sodium has a positive charge. This is called an ionic bond. Ionic. It's created between two ions, a metal, which is positive, and a nonmetal, which is negative. Three types of bond: ionic, covalent, and polar covalent. To be clear, these are intramolecular, not inter. These bonds are inside of the molecules. Any bond between two different elements is polar. The question is, how big is the polarity? And that is a discussion for electronegativity differences. That tells you how great the polarity is. Okay? This dipole moment is the bond polarity. And so it points toward the more electronegative atom. So for example, if I use carbon monoxide and I check my electronegativities, oxygen has a greater electronegativity, I would draw my dipole arrow running from the carbon to the oxygen, creating a partial, that's like a little D, it's called a delta, a partial positive and negative. This is only for bonds, not for molecules. When we get to, we're going to get to molecules in a little bit, but we're just talking about bonds between atoms right now. Okay, next, Lewis dot structures. How many of you have heard of them? Okay. So I have precise steps on how to draw them. A Lewis dot structure is for covalent electrons, bonds, covalent bonds, all right? Because they share. And so since they share, it's not a direct transfer. So remember that, like, for ionic bonds, I would have sodium, 1 valence electron, and chlorine, 7 valence electrons. The sodium would give its 1 electron over to chlorine. The reason is because chlorine is smaller, has a greater pull, has a higher electronegativity, lots of reasons, all right? And so then from here, you're going to go to Na plus Cl minus, which now has 8 electrons, and they're going to come together. Why are they going to come together? The positive and the negative charges are attracted to each other. So I'm going to end up with sodium chloride. This is how we do it. Okay. Which creates NaCl with a dipole headed toward the chlorine. This is an ionic bond. This is how we do ionic bonds, okay? We show the transfer of the electron. But with covalent, we don't have a transfer of electrons. So how do we do Lewis dot structures? So I have very specific steps, and we're going to do a couple practice problems using these very specific steps, okay? All right. First, hydrogen is always terminal, meaning it's always the end of the line. That's what terminal means, like, you know, a train terminal kind of thing. Train terminal, right? Always terminal. And it can only have 1 bond because it only has 1 electron. So therefore, it has to be terminal, right? Because it can't have anything else attached to it. Now, what I want you to think about is that we are always creating a wheel. As a rule, we're always creating a wheel. So the goal is what's inside the wheel, the center, and then what are the spokes around the wheel. So hydrogen is always around the wheel because it can't be the center because it only has 1 bond, right? If I'm in the center, I got to have, like, 3, 4 bonds given out to the spokes, right? But hydrogen can only have 1 bond, so it's got to be on the outside. Okay? Next. The least electronegative atom goes in the center. Now, this is on your periodic table to the left. I tell this to my honors students, but you guys should be able to figure it out, like just looking and seeing, oh, the right is the highest electronegativities in a row, so it's all going to kind of show up. The other thing is the formulas are going to indicate the wheel. So when you see SF6, there's 6 fluorines and 1 sulfur. What's going on the outside of the wheel? The fluorines, because the sulfur is only 1. There's only 1 sulfur. So it's the center of the wheel, and the fluorines are on the outside of the wheel. See how that works? You're always creating a wheel. Okay. Next, you're going to find the total number of valence electrons available. You're going to add them up. And then you divide by 2, and that tells you how many pairs you have to work with. Next, you place 1 bonding pair between each pair of atoms. So 1 bonding pair between, for example, sulfur and fluorine. 1 bonding pair between sulfur and fluorine. 1 bonding pair between sulfur and fluorine. So sulfur now has 6 things coming off of it. Right? Okay. Then, so 1 bonding pair. Then you use the remaining pairs to satisfy the octet rule. And we've done the octet rule. The octet rule says everybody gets 8 except who? Who doesn't need 8 electrons? Hydrogen. Everybody gets 8 electrons, access to 8. Access to 8 except for hydrogen, which only needs access to 2. to 2. And you can use lone pairs, double pairs, or triple bonds. Okay? Lastly, I'm all done. Everybody has 8, but I've got these 2 electrons left over. What do I do with them? Any excess electrons go around the central atom. All right? The central atom, many of them, including sulfur and phosphorus and selenium, have the ability for what is called an extended octet. This is an extended octet, which means it might have 12 electrons around it. Okay? How do you know if you have an extended octet? You're making the wheel, so you might have 6 fluorines around it, which right away is 12, and then there might be 1 pair left over, and the rule is that goes on the center atom. That's an extended octet. All right? You don't have to decide, oh, it's an extended octet. It'll tell you. So let's try some. I'm going to do the exact process that is here. Okay? Step 1. Hydrogen is always terminal, so I'm not going to worry about it because I'm looking for my wheel. So I see I have 1 nitrogen and 3 hydrogens. That tells me what goes in the center? Nitrogen. So the least electronegative atom, you can check, yup, the lowest electronegativity is going to be nitrogen. So nitrogen goes in the center. Then I place my hydrogens around. Next, find the total number of valence electrons. Okay, let's see. Nitrogen has 5. And then I have 3 hydrogens, so I have 3 times 1. So that's 5 plus 3 is 8 electrons. Are there questions yet? Okay. Now I'm going to divide by 2, and that's going to tell me how many pairs I have. Yep. So I take 8 divided by 2. I have 4 pairs to work with. Now I have to give everybody access to 8 hydrogen 2 using 4 pairs. That's what I have. All right? Izzy, you have a question?
Yeah, where'd you get the 3 from?
So the 3 is for hydrogen. There's 3 hydrogens.
Oh.
And they each have 1.
Okay.
So this here is I'm working with total valence electrons.
Okay.
I'm adding them all up. I'm throwing them in a pot. Throw them all in the pot. Now we're going to divvy them out. Bless you, bless you, bless you, bless you, bless you. Okay. Place 1 bonding pair. Bless you, bless you, bless you. Place 1 bonding pair. I think we should start like what time it happens. So we could say like, oh, it's 8:03. All right. So 1 bonding pair between each of the elements. And then I cross this out. I don't have 4 anymore. Now I have 1. Because I used 3. Everybody okay? Next, I double check my, use the remaining pairs to satisfy the octet rule. Okay. Hydrogen is good. It has access to 2 electrons. Hydrogen is good, has access to 2. Hydrogen is good, has access to 2. Nitrogen has access to 6. 2, 4, 6. I have 1 pair left. Now nitrogen has access to 8. So if I were to show you, I would say hydrogen, 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 nitrogen. And nitrogen is allowed to do that. They're allowed to do that. Why? They're sharing, so they can both claim those 2 electrons. That's the whole point. Yep.
You should only think about it in pairs.
Only think about it in pairs. Once, 15 years ago, there was a problem on the exam with 1 electron. And basically, the placement of the electron was discounted, and they had to give points to anywhere that you placed the electron as long as you got the rest of the structure right. Because it was 1 electron. It happens. And then the lowest electronegativity gets that electron. That makes sense. I mean, the highest electronegativity gets that electron, which makes sense, because it's going to pull it over there, right? Yeah.
Is the fact that the bonds, like one bonding pair goes to each atom, is that like the same as Hund's rule?
No.
Okay.
That's a good question. No. This is not a Hund's rule thing, but that's a great question. All right. Carbon monoxide. Here we go. No wheel, right? Just carbon and oxygen. Which has the lower electronegativity? Right. So carbon would be in the center, but there isn't one. Okay. So I have one carbon at 4 valence electrons. I have one oxygen at 6. That's a total of 10, which is divided by 2 is 5 pairs. I have 5 pairs to give everybody 8. So I'm going to connect. That's 1. Now I'm down to 4. Now I'll just take 4. 1, 2, 3, 4. Okay, did that work? No, it didn't work because carbon is not happy, right? So what we're going to do is we're going to take one of these and move it down here. So that's going to give me carbon with 1 pair, 2 bonds in the middle, oxygen with 2 pairs. Are we done? No. Carbon still isn't happy. See that? So I'm going to take 1 pair and move it in here. Because they can share. It's not changing oxygen, right? So now I have carbon, 1, 2, 3, oxygen. And there are my pairs, 10 pairs. Right? And everybody's happy. Oxygen has access to 8. Carbon has access to 8. Yeah.
Why did you start off by giving oxygen, like...
You could have given them to carbon.
It doesn't matter.
No, I just placed them down so I could see where they were. Yeah, just get them all on there and then do your count. So you place 1 bonding pair and then use the remaining pairs to satisfy the octet. So just put them down and then start moving around. Okay? All right. What about polyatomic ions? So polyatomic ions have a charge. Oh, time's up. Okay. All right. Well, yeah, okay. All right. So tonight you're going to have, wait a minute. Okay, so that we'll do polyatomic ions next. Okay. No, that's not